Hello. Hello. So next up is Batuhan. So we studied parabolic dynamics. Um, we first of all watched a series of lectures by Corina Ulcigray, and we learned a bunch of different theorems. But in this presentation, he's going to be focusing on sort of like the basics, and he's going to be talking about this specific theorem. And without further ado, please go ahead, Batuhan.
Okay, I'm Batuhan. Today I talk about time chains in parabolic dynamics. But before I start, I want to thank my mentor, Alpuzman, and the ERP organization team, all of you who attended this symposium. And the table of contents are dynamical systems. First of all, I define what dynamical systems are. And HAB classification of dynamical systems. There are three paradigm in dynamical systems, which depends on the matrices. Then the equivalence of dynamical systems. Under what condition two dynamical systems are equivalent? There are two signs in equivalence. And after that, I talk about time chains. Time chains comes from the equivalence in weak sense. I will talk about that. And there is a lemma about time chains. I will prove this lemma, and this proof is the only proof of the presentation. After that, there's a Heisenberg law. It's a parabolic dynamical example of parabolic dynamics. And I state a theorem about time chains and Heisenberg law. Start with what dynamical systems are. In order to talk about dynamical systems, we need a set. Dynamical systems consider a systems evolves with time. In order to talk about dynamical systems, we need a non-empty set. This set has some extra structure. So this set X could be metric space or manifold or something like that. And we need a group. Let's call it T. This T stands for time. This group could be integer under addition or real numbers under addition. And dynamical system is just group homomorphism, equivalent to a function, phi t times x to the x. If this group is integer, dynamical systems called discrete dynamical systems, but this t is r, real numbers, dynamical systems called continuous dynamical systems or just a flow. And there is a relation for the flow phi t1 plus t2x equal to phi t1 comma phi t2x. In a picture, there are 3 points x, y, z, and there is a flow. The trajectory x is phi 0x, y is phi t1x, z is phi t2x. This set could be stated in many ways, but in this picture, that equal to could be phi t2x or just phi t2 minus t1 y. So this shows that the flow is deterministic, which comes from the group property time parameter. And there are three paradigms in dynamical systems: hyperbolic dynamical systems, elliptic dynamical systems, and parabolic dynamical systems. In hyperbolic case, we need a 2x2 matrix. The main properties of this matrix is this matrix has two eigenvalues. The norm of one of the eigenvalues is less than 1, the other one is bigger than 1, which is hyperbolic matrix. And in elliptic cases, we have rotation matrix with irrational integers. In parabolic cases, P 1, 1, 0, 1, this is shear matrix, and whose eigenvalues is just 1. And sensitive dependence on initial conditions. Again, I can state three paradigms in by using STI, sensitive dependence on initial conditions, or deterministic cause. We have a matrix space X, and V is a metric on X. We say that the dynamical systems phi has sensitive dependence on initial conditions. If one can find a positive number kappa, such that any initial condition X has nearby point Y, such that at some time in the future, the distance between phi tx and phi ty is more than kappa. So the trajectory starts near y, and as time goes on, y at time goes on, distance gets separated. If such a kappa exists, it's called the sensitivity constant of the dynamical system. In a more formal way, there exists kappa for every x in x, epsilon, distance less than epsilon. There is a t such that the distance phi tx, phi t bar bigger than kappa. In the picture, 2 points, phi 0x, phi 0y, distance less than epsilon. These are trajectories of x and y. At some time later, distance bigger than kappa. But the question is how fast the distance increase. If the distance, let's define a g growth function, distance phi tx, comma phi ty. If the distance grows exponentially, the dynamic system is called hyperbolic. If the distance does not grow or grows subpolynomially, the dynamic system is called elliptic dynamic systems. If it grows polynomial, the function grows polynomially, dynamic system is called parabolic. These definitions are not exact. These are still debated, especially in elliptic case and parabolic cases. There is an example called Ehrenfest billiard. Some mathematicians said that this Ehrenfest billiard is elliptic dynamical systems with some singularities, and there are some mathematicians said that this Ehrenfest billiard has parabolic features. So we take as an example of parabolic dynamics. In our slides, Ehrenfest billiard is an example of parabolic dynamics. In discrete cases, we had a function, we had a matrices. When applied n times the hyperbolic matrix, we have 2 to the 0, 0, 1 over 2 to the. When we take a point in R2 in the plane and apply this, the 2 points get separated as time goes on. In elliptic cases, it's a rotation matrix again with irrational argument. And in parabolic cases, p to the n equal to 1 and 0, 1. So this is just a gross polynomial. Equivalence of dynamical systems. Then there is a two dynamic systems, phi and psi. There are two sense in the equivalence case. One of them is strong sense, the other one is weak sense. Phi and psi are equivalent in the strong sense. If there is an isomorphism phi, big phi, that takes the trajectories of one and gives another. Phi is the trajectories of one, psi is another trajectory with preserve the same time parameter. In weak sense, this time couldn't be preserved, another time parameter that we have. So in this case, big phi take phi and gives another trajectory, another phi, another psi. And phi and psi are equivalent in the weak sense, again gives the one flow, one trajectory, one dynamic systems, and give another dynamic systems. But in this case, this t in here, this is tau in here, that the function depends on x and t. In this isomorphism, the time parameter could be different. I mean, the time parameters change, the parameterize of time. Sometimes it just depends on t, sometimes it depends on x and t. And the time change comes from here. Phi and psi are weakly equivalent. They are also time changes of each other, or the parameterization of time. Also the function tau called time change. And we use this notation, phi equal to psi sub tau. And there is a lemma in here. This tau has to satisfy an algebraic equation. The algebraic equation is this. It's a co-cycle identity over the flow phi. Tau t plus s, comma x equal to tau t by sx, comma plus tau sx. Because this, and also this abbreviation, phi sub t equal to phi tx. Since phi and psi are orbit equivalent, we have this relation. And when we apply the big pi inverse from left, we have this relation. And by using the group property for phi, we have this. And this is the last slide equation. This is just this goes from previous slide. The phi t equal to big pi inverse composition psi tau tx composition big phi. In this case, on the left hand side, we have phi t plus sx, and we have big pi inverse composition phi tau t, phi sub tau t plus s, and in here we have t, and in s. And when we open this phi s, we have this, and there is a cancellation in here. This gives identity function, and we have third line, and from the group property of the two side, we have fourth line. Just add them up these taus. In the left hand side, we have this. In the right hand side, we get this. By cancelling phi's out, we have this psi tau sub tau equal to this psi sub tau plus another tau. So these tau must be equivalent. We assume this condition. If psi t0y equal to psi t1y, implies that t0 must be equal to t1. This is always the case that we are interested in dynamical systems. A time change is called trivial if this if the equivalence is strongly equivalent, and time change to whether or not a time change is trivial is a cohomological problem. Small time change of a parabolic dynamic systems is also parabolic. Time change is not strongly equivalent to the original system, and by using time change, we get another parabolic system, new parabolic dynamical systems. And there are statistical properties, mixing, weak mixing, and ergodicity, unique ergodicity. And now these statistical properties, let's say X is a manifold and mu is a probability measure on X, invariant under dynamics of psi. So that X0 is the initial point. We said that the trajectory X0 is equidistributed if this equation holds. F is a continuous function. On the left hand side, this is the time average. In the right hand side, this is space average. Since the group parameter group T is R, there is an integral in here. If the group is integer, this could be this integral signs should be sigma for showing the summation. And by using this equidistribution definition, we define ergodicity and unique ergodicity. Mu is dynamical systems is ergodic if almost every X is equidistributed in the space. In uniquely ergodic, if X is equidistributed for every initial condition. The difference is in ergodic cases, almost every initial condition, in uniquely ergodic cases, every initial condition X. And the flow psi is mixing in strong sense. If for any two functions f and g, as t goes to infinity, these limits converge to this. There is a multiplication here, f times g, but f takes a trajectory, and there is a multiplication again, but f d mu, f d mu, two different integrals. Nuclear ergodic and mixing are strong property. Nuclear ergodic implies ergodic, but not vice versa. Mixing also implies ergodic, but not vice versa. But uniquely ergodic and mixing independent properties. They are not implies each other. For both mixing and unique ergodicity stronger than ergodicity. And in hyperbolic dynamical systems, there are three cases: uniform hyperbolic, partial hyperbolic, non-uniform hyperbolic. Following this theory, we have uniform parabolic, the categories uniform parabolic, partial parabolic, non-uniform parabolic. For cycle flow is uniform parabolic examples. Partial parabolic cases, we have Heisenberg flows, and non-uniform parabolic Theorem continues. That the base goes on in the definition of the previous slides. And I talk about Heisenberg flows. First of all, we need a space. So we define a Heisenberg group M. It's a 3x3 matrix, X, Y, and Z. These X, Y, Z are elements of real numbers. And there's a gamma, discrete subgroup of N. This gamma again same matrix, but in this time X, Y, Z should be integer. Heisenberg manifold, our space, is the compact quotient of M equal to N mod gamma. And we define the Heisenberg flow. This is the flow phi sub phi upper W. This is P is an element of M, P times exponential P times W. This W is an element of the B algebra of Heisenberg group M. And size any Heisenberg flow is measured preserving. And some Heisenberg flows are uniquely ergodic, some are not. And Heisenberg flow is never mixing. And I state a theorem, recent theorem about this topic. Consider the Heisenberg manifold M and take a unique ergodic flow H on manifold, Heisenberg manifold. There is a countable dimensional dense linear space of time chains, such that the subspace of A consisting of trivial time chains is countable dimensional, and any non-trivial time change tau in A, H tau is mixing. Smooth time change is infinite dimensional tau, smooth trivial, infinitely differentiable, big part and term. All about Python.
Thanks for this presentation. Are there any questions?
Yes.
In equivalence of dynamical systems part, there was a proof about the statement.